Imagine holding something lighter than aluminum, stronger than steel, and trusted inside rockets, race cars, and fighter jets every single day. But here's what nobody tells you. This incredible material doesn't begin inside a high-tech lab. Its story starts with ordinary-looking chemicals. Before this fabric becomes nearly 5 times stronger than steel by weight, it survives temperatures hot enough to reshape its very structure. Think about this. Thousands of tiny strands, each thinner than human hair, work together to lift airplanes and protect astronauts. Every single strand follows an astonishing journey stretching across continents before reaching the world's most advanced manufacturing plants. Most people never think about this, but one invisible mistake during production can weaken an entire aircraft component forever. That explains why every meter of carbon fiber undergoes relentless testing long before engineers trust it inside life-saving machines. And this is where it gets truly extraordinary. The world's strongest fibers begin as soft, flexible threads anyone could easily bend. Over the next 15 minutes, we'll follow every transformation, every machine, and every hidden secret behind this engineering miracle. But first, we need to uncover where these remarkable fibers are actually born, because the answer surprises even experienced engineers. Most people assume carbon fiber begins as pure carbon pulled from deep underground. The truth is far more surprising. It starts with a synthetic plastic called polyacrylonitrile, better known as PAN, which accounts for more than 90% of the world's carbon fiber production. The journey begins in massive petrochemical plants, where crude oil and natural gas are transformed into the chemicals needed to create PAN precursor fibers. Every batch must reach exceptional purity because even microscopic impurities can weaken the final material. Countries like Japan, the United States, Germany, South Korea, and China produce some of the world's highest quality precursor fibers. These facilities operate around the clock, supplying advanced factories that serve aerospace, defense, automotive, and renewable energy industries. Inside the chemical plant, acrylonitrile monomers are carefully purified before entering a controlled polymerization process. Long molecular chains begin to form, creating the foundation for one of the strongest engineering materials ever invented. The liquid polymer resembles thick syrup before it is pumped through thousands of microscopic spinneret holes. As each strand emerges, it instantly begins transforming into an incredibly fine precursor fiber thinner than a single human hair. These delicate white fibers travel through washing, stretching, and drying systems designed to align their molecular structure. This invisible alignment determines how strong the finished carbon fiber will eventually become. Once prepared, the precursor fibers are wound onto enormous precision spools, each containing hundreds of kilometers of continuous filament. Every spool is carefully protected from dust, moisture, and contamination during transportation. Specialized trucks, rail networks, and cargo ships carry these valuable spools across continents to carbon fiber manufacturing plants. A single damaged spool can cost thousands of dollars and delay production for weeks. What surprises many engineers is that the precursor accounts for more than half the total production cost. Before the fibers ever enter a furnace, manufacturers have already invested enormous amounts of time, energy, and precision. Producing these raw materials also demands significant energy and careful environmental management. Modern factories recycle solvents, reduce emissions, and recover heat wherever possible, helping lower the environmental footprint without sacrificing quality. Every shipment undergoes rigorous inspection before entering the factory. Technicians measure fiber diameter, moisture content, chemical consistency, and tensile properties to ensure every spool meets strict manufacturing specifications. Only after passing every inspection does the real transformation begin. In the next stage, these soft white threads will enter blazing furnaces reaching temperatures hotter than molten lava, where they will permanently become carbon fiber. Inside the factory, the real transformation finally begins. Soft white precursor fibers unwind from enormous precision spools and travel through a carefully controlled production line at a constant speed, where every second determines the quality of the final product. Before any carbon forms, the fibers pass through an oxidation furnace heated between 200 and 300 degrees Celsius, or 392 to 572 degrees Fahrenheit. Oxygen slowly reacts with the polymer, locking the molecular chains into a heat-resistant structure that can survive the extreme temperatures ahead. The oxidation stage lasts anywhere from 30 minutes to 2 hours, depending on the fiber grade and thickness. During this time, powerful fans circulate heated air while sensors continuously monitor temperature, airflow, and tension to prevent even the slightest defect. Next comes the most dramatic stage of the journey. The stabilized fibers enter a carbonization furnace filled with nitrogen instead of oxygen, preventing the material from burning while exposing it to temperatures between 1,000 and 1,500 degrees Celsius, or 1,832 to 2,732 degrees Fahrenheit. As the temperature climbs, nearly every element except carbon escape from the fibers as gases. Hydrogen, oxygen, and nitrogen atoms separate from the molecular chains, leaving behind tightly bonded carbon atoms arranged in incredibly strong microscopic crystals. The furnace glows with intense orange light while the fibers move continuously through its center at carefully controlled speeds. Every meter must experience exactly the right amount of heat because even a slight variation can reduce strength and durability. For aerospace-grade carbon fiber, some manufacturers add a second high-temperature graphitization stage reaching nearly 2,500 to 3,000 degrees Celsius, or 4,532 to 5,432 degrees Fahrenheit. This process aligns the carbon crystals even more precisely, creating exceptional stiffness and performance. Once the heat treatment is complete, the newly formed carbon fibers emerge deep black with a smooth, glossy appearance. Although each filament measures only about 5 to 7 micrometers in diameter, it possesses remarkable strength far beyond ordinary metals of similar weight. The fibers then travel through a surface treatment process where electricity and specialized chemical solutions gently roughen the outer layer. This microscopic texture allows epoxy resins and composite materials to bond securely during later manufacturing. Immediately afterward, a protective sizing coating is applied. This ultra-thin polymer layer shields the delicate fibers from damage during handling while improving compatibility with different resin systems used in aerospace, automotive, and sporting equipment. The coated fibers enter high-speed drying ovens before moving to automated winding machines. Thousands of perfectly aligned filaments combine into continuous tows containing anywhere from 1,000 to more than 50,000 individual carbon fibers. Robotic winding systems operate with extraordinary precision, maintaining constant tension while wrapping the finished fiber onto perfectly balanced spools. Laser sensors continuously measure diameter, alignment, and winding quality throughout the process. Every completed spool receives a unique identification code that records its production date, furnace temperatures, processing speed, chemical batch, and inspection history. This digital traceability allows manufacturers to track every meter of fiber throughout its entire life cycle. Before leaving the factory floor, samples from every production batch undergo tensile strength testing, microscopic inspection, and dimensional analysis. Only material meeting the strictest engineering standards earns approval for use in aircraft, spacecraft, racing vehicles, and advanced industrial products. What looks like an ordinary black thread has now completed one of the most demanding manufacturing journeys on Earth. But before engineers trusted inside billion-dollar aircraft or life-saving spacecraft, one final series of extraordinary quality tests still awaits. The manufacturing process may be complete, but the real challenge is only beginning. Before a single strand of carbon fiber reaches an aircraft or racing car, it must survive some of the toughest quality inspections in modern industry. Every finished spool enters a fully automated inspection system where high-speed cameras, laser scanners, and AI vision technology examine thousands of individual filaments every second. Even the smallest surface defect is instantly detected and recorded. Powerful laser sensors continuously measure the diameter of every fiber with microscopic precision. The acceptable tolerance is often less than 1 micrometer, and anything outside that limit is immediately rejected. Advanced machine vision systems compare each spool against a digital reference model. They search for broken filaments, contamination, uneven coating, discoloration, and microscopic cracks that the human eye could never detect. The factory's central control system collects millions of data points every hour from temperature sensors, pressure gauges, tension monitors, and production equipment. Artificial intelligence analyzes this information in real time, preventing defect before they can spread through an entire production batch. Not every spool passes inspection. Depending on the product grade, rejection rates typically range between 1 and 5%. Aerospace-grade carbon fiber follows even stricter standards, where perfection is the only acceptable result. Next comes mechanical testing. Sample fibers are clamped into hydraulic tensile testing machines that pull with incredible force until the material finally breaks. Engineers carefully measure tensile strength, elasticity, and ultimate failure points. Other samples enter fatigue testing machines where they are bent, stretched, and compressed millions of times to simulate years of real-world service. Components used in aircraft must prove they can survive decades of repeated stress without losing structural integrity. Environmental testing is equally demanding. Carbon fiber samples spend days inside chambers exposed to freezing temperatures, extreme heat, high humidity, ultraviolet radiation, and corrosive chemicals. Only materials maintaining their strength under every condition receive final approval. Microscopes capable of thousands of times magnification reveal the internal structure of each filament. Quality engineers inspect crystal alignment, resin bonding surfaces, and microscopic imperfections invisible to ordinary optical equipment. Although automation performs most inspections, experienced technicians still make the final decision on critical aerospace materials. Years of training allow them to recognize subtle patterns and surface characteristics that even advanced artificial intelligence occasionally overlooks. Every approved spool receives complete digital certification, including production history, furnace temperatures, inspection records, laboratory results, and traceability information. This permanent record follows a material throughout its entire service life. Only after passing every inspection does carbon fiber earn its place inside passenger aircraft, spacecraft, Formula One race cars, military equipment, medical devices, and wind turbine blades where failure simply cannot be tolerated. It is remarkable to think that thousands of inspections, countless measurements, and years of engineering expertise stand behind a material that most people notice only as a sleek black surface. But one fascinating question still remains. After traveling through chemistry, fire, automation, and relentless testing, just how much carbon fiber does the world actually produce each year, and which countries lead this extraordinary industry? That answer is even more surprising. Did you know the global carbon fiber industry now produces well over 100,000 metric tons every year, yet demand continues to grow even faster than factories can expand? The global carbon fiber market is already worth several billion US dollars and is projected to more than double over the next decade as electric vehicles, commercial aircraft, wind energy, and space exploration require lighter and stronger materials. China has become the world's largest producer, accounting for roughly one-third of global carbon fiber manufacturing capacity. Massive investments in new factories continue to increase its share every single year. Japan remains one of the industry's technology leaders, producing some of the highest quality aerospace-grade carbon fiber through decades of engineering innovation and precision manufacturing. The United States plays a critical role by supplying advanced carbon fiber for military aircraft, spacecraft, satellites, and next-generation commercial aviation, where performance matters more than production volume. Germany combines advanced engineering with automated manufacturing, supplying premium carbon fiber components to luxury automobiles, industrial machinery, and high-performance engineering industries across Europe. South Korea continues expanding rapidly with major investments in research, automation, and high-strength carbon fiber production, becoming one of the fastest-growing suppliers in the global market. Worldwide, hundreds of thousands of engineers, scientists, technicians, machine operators, and quality specialists work across the carbon fiber supply chain, from chemical plant to aerospace assembly lines. More than 50 years ago, carbon fiber remained an experimental material used only in specialized laboratories. Today it supports entire industries that depend on lightweight, ultra-strong engineering materials. Modern passenger aircraft use thousands of kilograms of carbon fiber composites, reducing fuel consumption while increasing structural strength and improving long-term durability throughout decades of service. Wind turbine blades stretching longer than a football field rely on carbon fiber reinforcement to remain light enough for efficient rotation, while surviving years of extreme weather and continuous stress. Formula One engineers depend on carbon fiber monocoques capable of protecting drivers during crashes involving enormous impact forces while keeping racing cars incredibly light and exceptionally fast. Here's something astonishing. Pound for pound, high-quality carbon fiber can be several times stronger than structural steel while weighing only a fraction as much, completely transforming modern engineering design. Looking ahead, researchers are developing recyclable carbon fiber, bio-based precursor materials, faster production methods, and smarter automated factories that could dramatically reduce manufacturing costs over the next decade. The next time you hold a carbon fiber product in your hands, remember that behind its sleek black surface lies decades of scientific discovery, billions of dollars in innovation, and one of the most extraordinary manufacturing journeys ever created. If you enjoyed this journey inside the world of carbon fiber manufacturing, don't forget to like this video and subscribe to the channel for more incredible factory documentaries. Tell us in the comments which product or factory you'd like us to explore next. Your suggestion could become our next behind-the-scenes adventure. Thank you for watching, and until next time, stay curious, keep learning, and we'll see you inside the next factory.